In this video, we will go over an intuitive overview of the concept of ventilation and perfusion of the respiratory system, which will help explain why we have a non-zero physiological AA gradient, as well as, toward the end, we'll go over some common pathologies that lead to a greater AA gradient as a result of ventilation-perfusion or VQ mismatches. In a perfect world, where our bodies are able to fully oxygenate all of the blood that comes to our lungs, and barring any other structural heart issues or other natural shunts like we will talk about at the end, the AA gradient would be zero because all the blood that came into the lungs would get enough oxygen to equilibrate with the oxygen available in the alveolus, thus making the difference between the oxygen level in the arteries equal to the oxygen level in the alveoli. However, this is clearly not the case, as healthy people have an AA gradient of about 10 millimeters of mercury of oxygen. The cause of this gradient is due to a concept called ventilation-perfusion mismatch, and the ventilation-perfusion ratio is one of the things that can help represent how efficiently the lung is transferring the oxygen that it has breathed in. Before we get into details, let's first go over the general concept of what I mean when I say the efficiency of oxygen transfer. Imagine in this example, our blood is composed of one red blood cell, and that one red blood cell only has one hemoglobin molecule, which has the capacity to carry 4 oxygen molecules total. When this red blood cell makes it to the capillary alveolar interface in the lung, it tries to pick up as much oxygen as possible. Let's say for this example, there was conveniently exactly 4 molecules of oxygen waiting to be loaded onto the red blood cell. Then, all 4 of the oxygen molecules would, as expected, get loaded onto the red blood cell, which then goes on its way to hand that oxygen off in the body wherever it is needed. In this case, the hard work that the heart did to pump that red blood cell to the lungs, and the hard work that the lungs did to bring those oxygen molecules are completely used to their full capacity, and thus maximizing efficiency. Let's say instead of having 4 oxygen molecules waiting to be loaded, there are only 2 oxygen molecules there because maybe the air didn't have enough oxygen to begin with or something along those lines. In this scenario, when the red blood cell makes its way to the capillary alveolar interface, it's only able to load the 2 oxygen molecules, leaving the hemoglobin only half filled. This means that half of the effort of bringing the blood to the lung was wasted, hence this scenario is inefficient. Let's say this time we have 8 molecules of oxygen, and we have the same one red blood cell with one hemoglobin molecule that makes its way to the alveolar capillary interface to pick up oxygen. You can probably already tell what happens here. The hemoglobin picks up 4 oxygen molecules, and the alveolus is left with 4 molecules of oxygen that couldn't be picked up. Thus, effectively half of the work that the lungs did to breathe in the oxygen was wasted. Hence, this scenario is also inefficient. With these examples, we can easily think of a solution to make these more efficient. We can reduce the amount of blood going to areas with less oxygen so that less blood is wasted, and increase the amount of blood going to areas with more oxygen so that less oxygen is wasted. Luckily, our lungs do just that. Our lungs are kind of like those slinky toys that you may have played with when you were younger or had the pleasure of using for a physics experiment in school when you learned about longitudinal waves. When this slinky is held upright in the air by its end, you would recall that they stretch out like this, with the top portion spread out the most and the bottom portion being the most compressed. This makes sense because the higher portions of the slinky has to carry the weight of the rest of the slinky below it, thus has a greater force stretching the slinky downwards compared to the lower portions, which has only a little bit of slinky to hold up. When you pull that slinky down, the slinky would of course stretch out more, but it is important to note that most of the stretching happens toward the bottom of the slinky. This is because the top portions are already pretty stretched and need a lot more force to stretch it even more compared to the bottom. For those of you who want to be reminded of the equation illustrating this phenomena of springs, it's the equation where K is the spring constant determined by the stiffness of the spring, and X is the displacement from the spring's equilibrium length. As the spring is stretched, the greater the displacement from its equilibrium, and thus the spring needs more force to stretch it even further. Our lungs behave much like the slinky in that the top of the lung is disproportionately more stretched compared to the bottom portions of the lungs. Just like how the slinky was more stretched at the top, The greater stretching of the lung toward the top results in the alveoli of that area being stretched open more at baseline compared to the bottom. This is important because that means when you take a deep breath, the diaphragm pulls the lungs downward to expand the lung, and the majority of the new air that's breathed in goes to the bottom portions of the lung where the greatest amount of expansion occurs. This is just like how when the slinky was pulled downward and the majority of the stretching occurred toward the bottom of the slinky. The top portions of the lung also get new air, but not as much, as the alveoli are already pulled open at baseline and can't really expand that much more to allow new air to come in. In our medical lingo, we say that there is high ventilation at the bottom of the lungs, meaning that lots of new air is cycled through the lower lungs, and there's low ventilation at the top of the lungs, meaning that little new air is cycled through the upper lungs. Now that we've established that most of the new air, and hence new oxygen, goes preferentially towards the bottom of the lungs, we can see that the way that the oxygen is distributed throughout the lung is the same as the example we looked at the beginning. When we track the distribution of blood, or perfusion, in the pulmonary vasculature, we see that most of the blood goes to the lower portions of the lungs because of gravity. In medical lingo, we say that the lower lungs are highly perfused, while the upper lungs are less perfused. This is actually great news because this means that our lungs have set up a system that automatically directs lots of air to the places that naturally get a lot of blood and less air to places that naturally get less blood. So you may be wondering, what gives? Why is there inefficiency? The reason is that the increasing amount of ventilation that we see in the lungs as we go toward the bottom of the lungs is not exactly proportional to the increasing amount of perfusion as we go toward the bottom of the lungs. Graphically, it would look something like this. Both ventilation and perfusion increase as you go down the lung, but perfusion increases at a greater rate. Here, we see that somewhere in the middle of our lungs, we have the perfect 1-to-1 ratio of ventilation and perfusion for perfect efficiency. However, at the top of the lung, we have more ventilation than perfusion, thus air is wasted. Again, this means that we have more oxygen available at the top of the lung than the blood can feasibly carry, so there's unused oxygen up there. This is mathematically represented with a ventilation-perfusion ratio of greater than 1. At the bottom of the lung, we have more perfusion than ventilation, thus blood is wasted. Again, this means that we don't have enough oxygen at the bottom of the lung to saturate all of the hemoglobin in the blood that's going there, so we have unused oxygen carrying capacity. This is mathematically represented with a ventilation-perfusion ratio of smaller than 1. We give these two types of inefficiencies some fancy names called dead space and shunts. Dead space describes the inefficiency where air is wasted. I imagine we call it dead space because we can illustrate this inefficiency like this. Here, we have the same wasted air inefficiency, but illustrated in two different ways. The illustration on the left illustrates what actually occurs in the lung, but we can break this up into two alveoli where one is getting perfect efficiency and the inefficient portion is lumped all into the other alveolus. When represented like this, where the average represents what's happening overall, the alveolus that represents the inefficiency shows just oxygen hanging around with no access to blood. Thus, it is space that makes no contribution to oxygenation, which we can call a dead space. Just as another example, the air in the trachea is also called dead space because it too has oxygen that makes no contribution to the oxygenation of blood. Shunts describe the inefficiency where blood is wasted, or more accurately, the oxygen binding capacity is wasted. This is called a shunt because we can illustrate the inefficiency like this, where we have one alveolus and capillary combo with perfect efficiency and another capillary with no interaction with an alveolus. This blood might as well have bypassed the lungs completely and gone directly from the right heart to the left heart. Because this blood basically bypassed the lungs with regards to oxygenation, we say that this blood was shunted. With all of this being considered, the normal VQ ratio of a healthy adult is about 0.8, so there's a net effect of some shunting going on. Lastly, we'll end with some examples of diseases that lead to increased dead space or increased shunting. The classic example of dead space is a pulmonary embolism. A clot causes the blockage of blood from perfusing certain capillaries. Thus, the alveoli that are paired with those capillaries will be ventilated without any blood going to them to pick up the oxygen it provided. Another example of dead space would be emphysema, where the alveoli become damaged and kind of distended. Because the surface area to volume ratio goes down, the air that's in the center of the distended emphysematous alveoli won't be able to oxygenate the blood, thus leading to a wasted ventilation, or high VQ ratio. The classic example of shunting would be pulmonary edema or pneumonia. Stuff fills up some of the alveoli, thus effectively knocking out the function of those alveoli. The blood carried to the capillaries that are paired with those plugged up alveoli are not oxygenated and effectively shunted. I have written out the main takeaways here. A VQ ratio of 1 represents perfect balance of ventilation and perfusion, whereas a VQ ratio greater than 1 means that there's some dead space physiology going on. A VQ ratio less than 1 means there's some shunting physiology going on. The fact that the ventilation-perfusion ratio is about 0.8 means that there's a net effect of shunting going on. This is one way to evaluate and see why the alveolar arterial gradient, or AA gradient, is not 0, because of the inefficiency in the lung in transferring oxygen to the blood. I hope this video was helpful. Bye.